name's Joe Gould.
I'm Courtney Pittman.
And hi, I'm Delaney. I'll be the person that'll be writing in the background, so you might not see me, but I promise you I'm there.
I'm going to define standing wave. Standing wave is reflections. Yep, reflections from parallel surfaces, and they're in constant position. And then compression is when the particles are really close together, and it's also high pressure. And has a lot of density, whereas rarefaction is where the particles are farther apart and have less density and have low pressure.
I'll be defining harmonics and overtones. So essentially, harmonics are just layered pitches to the original sound source. Essentially, the sound that you can hear right off the ear can be the fundamental sound, and then overtones is the scale of the harmonics. Then I'll define the in phase and out of phase. So like to start off, phase is just determines where the position of the waveform starts. And the difference between in phase and out of phase is that when two identical sounds are out of phase within like 180 degrees, it'll cancel out entirely. Whereas if two identical sounds were in phase of like 90 degrees, it would double in amplitude. So I'll define timbre. It's essentially the quality that is associated with the pitch or amplitude of sound. You can determine it by the shape of its waveform.
And then amplitude is the height of the wave or energy, and it's measured in decibels, and it's perceived as loudness or volume.
Hi, so I will be defining what propagate is and what frequency is. And so for starters, propagate or propagating is basically the sequence of waves that go through the air and hits different types of materials or mediums. So when you're thinking about sound traveling in the air, it's either going to reflect off of a surface or refract off a surface. And so that's kind of just what propagating is it being traveled within the air. And then frequency is the physical property of pitch. They're kind of like, they go hand in hand. It's measured in hertz, and so if you want to find the frequency of a sound wave, you can just take hertz or frequency, and then it'll equal to the velocity divided by the wavelength, and that's how you would find it. So in taking the dimensions of the room, we got that it's 5 feet is the width of the room on its x-axis, while it's 19 feet is the width of the room on its y-axis, and then 7 feet is just the length of the room. And so by using the equation from the original PowerPoint, we got that hertz equals 1,130 velocity over wavelength. And in doing the calculations, we just added up the dimensions of the room, which is 31. And so when taking the 1,130 divided by 31, we get about 36 hertz. And so then we multiplied it by 2 to try to match the sound wave. But in doing so, we realized that the loudness wasn't matching the pitch of the standing wave. And so we just continued to multiply it by 2 until we got that octave that we were looking for. So we had to do that about 6 times. But eventually we got the reverb, which is what we wanted. And here in this picture, you can see that this is the standing reflection of the wave that we calculated.